everyone!
Doris
And Anna here.
Today we are going to explore the theory of length contraction, as well as the idea of time dilation.
Well, you may never heard of this topic before, but this was one of the most significant theory being part of Einstein's special relativity in the physics world. First of all, time dilation, essentially stating how the faster you move, the slower time passes, not only relates to simply the measure of time but length as well.
Throughout this lesson, you will realize that when you approach the speed of light, the measurement of space changes, just like time. To further elaborate, if a person on Earth and a person on a spaceship in motion compare their spans of time for the same event, they must have different distances since the relative velocity between them stays the same. In other words, the faster you go, the smaller object it appears to be. Therefore, shorter the distance you perceive yourself to be traveling. This leads us into the ultimate phenomenon of the occurrence, length contraction.
To explain length contraction, let's compare two scenarios of a spaceship traveling at a high speed to a faraway object. In first version, we are looking at spaceship as an observer standing on Earth, and in the second version, we see things using the perspective as someone in the spaceship. As observers standing on Earth, we see the spaceship traveling at a certain velocity, v, while time flows normally, and the distance for the journey of the spaceship will label as L0, being the proper length. To emphasize, we are at rest with respect to the object that mark the distance, which are the Earth and the faraway object. In this case, the faraway object is the destination.
In the second scenario, we are on the spaceship, which means the only constant or what stays the same is the relative velocity v. However, in this case, it represents the velocity of Earth and the destination, as they move in respect to the spaceship. Because this velocity stays the same for observers on Earth, everything else would be different. Due to time dilation, time would turn into delta t0 instead of delta t, being the change of time, while the distance labeled as L0 would become L, being the contracted length of the journey.
The ratio of proper length and the contract length lies within the equation. L equal L0 times square root of 1 minus velocity square divided by speed of light square.
Not only do the two scenarios indicate different magnitudes for the length or distance of the journey, the length of the spaceship also differs. The observer standing on Earth will see a much shorter ship than what the astronaut in the ship actually sees.
This destination in length proves how two observers in these two scenarios portray different rates within the passage of time. From other studies, length contraction constructively explains the phenomenon behind how certain fast-moving particles define expectations, since during such speeds, time slows down and distance contracts, just like how the spaceship we observe from Earth seems to be moving slower.
Next, let's identify these values for delta t and L through this animation of the two scenarios we mentioned earlier. Delta t0 occurs in the second scenario when you are moving with the ship. As the frame moves with the ship, its arrival and departure both occur at the same location. This time interval is measured by the inertial reference with Earth and the faraway object mentioned earlier in the example. Observers on Earth will definitely measure a longer time interval, delta time, for this journey.
L0 is the proper length mentioned in the first scenario, measured by the observer who is at rest with the departure and arrival. In the spaceship journey, the perspective with respect to the start and end points, such as the observer on the spaceship, will register a short length for distance L, which means the proper length and time is not always the same since the perspectives are not. Now, let's look at some example. Scenario 1.
A space vehicle that is 30 meters long is traveling at a constant speed of 0.66 c past an observer standing on Earth. How long does the space vehicle appear to the observer?
Now let's look at some information we know. We know that LO is equal 30 meters, and the velocity squared divided by speed of light squared is equal 0.66 speed of light. So now what we have to do is use the 30 meters times the square root of 1 minus the velocity squared divided by speed of light squared. So 30 meters times 1 minus 0.66 square root is give us the answer of 33 meters. And now let's look at scenario 2. A space vehicle is traveling at a constant speed of 0.88 c, parallel to a wall that is 115 long. How long does the wall appear to an observer inside the vehicle?
So this question is looking for the contracted length given by the information. So the proper length is 150 meters, and the ratio of velocity squared over speed of light squared is 0.88 c. After plugging into the equation, you should get the answer of 55 meters. And that's our interpretation on the topic of length contraction, including time dilation.
Thank you for listening, and we hope our lesson taught you something more today.